Hi, I'm Cheryl Leach. In this video, we're going to look at two different ways to numerically approximate the definite integral from 0 to 1 of 1 over 1 plus x squared dx. We're going to be using the trapezoidal rule and Simpson's rule. Well, there are several similarities between these two rules and also some differences. So let's begin by looking at the similarities. When you're using both the trapezoidal rule and Simpson's rule, you're going to break your interval into subintervals, and you're going to want to find the length of those subintervals. We call that delta x. And we'll do that in either case. All right, well, what's another thing that's common to both of them? Well, once you find what those subinterval values are, you're going to want to evaluate the function at those points. So I'm going to want to find out what the function value is at those endpoints. And again, we'll do that regardless of which technique we use. So those are some of the similarities, finding the subinterval endpoints and the function values at those endpoints. Well, what are the differences? Well, the differences are in how you find the area under a curve. For the trapezoidal rule, you'll take these two function values and you'll connect them with a straight line. That creates a trapezoid. And so you'll be able to calculate the area of that trapezoid, sum up all of the trapezoids, and get an approximation of the area under a curve, which we know is the same thing as a definite integral as long as that curve is above the x-axis. Well, how is Simpson's rule different? Well, instead of looking at trapezoids, we're going to have these three function values that we have found, and we're going to connect them with a quadratic, in other words, a parabola. So if we connect these dots with a parabola, we can see that you can use this parabola to approximate the area under the curve, again, giving us an approximation for our definite integral. All right, so let's see how this all fits together. First, we're going to look at those common points. So the subinterval endpoints. In my particular example, I'm going from 0 to 1. Well, before I get those endpoints, I need to know how wide the interval is. So I can calculate delta x by saying that that's b minus a divided by n. In this case, it will be 1 minus 0 all over 4, or 1/4. So, my subinterval endpoints, my x sub 0 is going to be the leftmost endpoint, which in this case is a 0. X sub 1, I have to move a quarter of a unit. So that'll happen at 1/4. X sub 2, I move another quarter of a unit, so that puts me at 1/2. X sub 3 will be at 3/4, and x sub 4 will be at 1. And I've accounted for my entire interval from 0 to 1. All right, well, I've really just marked off those endpoints of my subintervals. What I really want are the function values at those locations. So let's go ahead and find out what f of 0 is. F of 0, when I plug it into my function, I'm going to have 1. F of 1/4, well, let's see. I'm going to have 1/4 squared, that's 1/16. So I'll have 16/16 plus 1/16, or 17/16, and when I invert and multiply, I get 16 over 17. Now we're going to plug in 1/2. When I plug in 1/2, I get 16 over 20. Again, this is just number crunching at this point. When I plug in 3/4, I'm going to get 16 over 25. And finally, when I plug in 1, I'm going to get 1/2. Okay, so those are the pieces that I need for my trapezoidal rule and Simpson's rule that are common to both. Now, the formulas are not going to be exactly the same because I'm using trapezoids and parabolas. So where's the difference? Well, we're going to be using some coefficients for the trapezoidal rule, and they'll be different than the coefficients that I use for Simpson's rule. Now, the first constant that's outside in my trapezoidal rule is b minus a divided by 2n. And for Simpson's rule, the constant out front is b minus a over 3n. So I want to keep those in mind. We're going to take different coefficients and multiply them by these function values. For the trapezoidal rule, the first one, the coefficient is 1, and so is the last one. But all of the pieces in between will have coefficients of 2. For Simpson's rule, we begin and end with a 1. However, in between, we alternate between 4s and 2s. So we'll have a 4, a 2, and a 4, followed by a 1. All right, now how does this all get put together? Let's take a look at the trapezoidal rule first of all. We're going to be looking at the integral from 0 to 1 of 1 over 1 plus x squared dx. And it's going to be approximately equal to the trapezoidal rule, b minus a all over 2n times the quantity. Now we're going to be looking at these function values and adding them up, but we're going to multiply by the constants that I have out front. So I'm going to have 1 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2 times f of x sub 3, and finally 1 times f of x sub 4. Okay. Now, for this particular problem, let's see what all these values are. Well, we know that b is 1 and a is 0, and we know that n is going to be 4. F of x sub 0, well, I've already calculated that. That's going to be 1. F of x sub 1 is 16 divided by 17. But remember, I have to mark this as 2 times 16 divided by 17. F of x sub 2 is 16 over 20. But again, 2 times that value. F of x sub 3 is going to be 16 over 25. But again, 2 times 16 over 25. And finally, my f of x sub 4 is 1/2. Now, at this point, we're going to have a bit of number crunching to do. But when you get this all entered into your calculator, you're going to end up with approximately 0.783. All right, that's the trapezoidal rule. Now we're going to move on to Simpson's rule. So Simpson's rule states that if we want to integrate from 0 to 1, 1 over 1 plus x squared dx, we can use the formula b minus a divided by 3n times the quantity. F of x sub 0 with a coefficient of 1, so that's just f of x sub 0, plus f of x sub 1, but this time the coefficient needs to be 4. So we'll have 4 times f of x sub 1. Next, we'd like f of x sub 2, but I need a coefficient of 2. So 2 times f of x sub 2. Next term will be 4 times f of x sub 3. The last term is f of x sub 4. Notice it only has a coefficient of 1. So we just have f of x sub 4. Now let's take a look at what all these individual pieces are. Well, we know that the b is 1 and that the a is 0. And we know that n is 4. F of x sub 0, We've already calculated that to be a 1. f of x sub 1 is 16 over 17, but don't forget your coefficient of 4. So that's 4 times 16 over 17. The next term, f of x sub 2, that's going to be 16 over 20. But again, don't forget the coefficient, so 2 times 16 over 20. F of x sub 3, that's going to be 16 over 25. So we have 4 times 16 over 25. And finally, the f of x sub 4 is going to be 1/2. And at this point, we have some number crunching to do again. However, when you plug all of that in, you're going to get approximately 0.785. So, 2 different answers, 2 different approximations. I hope this is helpful. Thanks.